Hi everyone. So for this week's R video, we're going to pretty much replicate the same X-Prep assignment that you submitted earlier this week, or really that's closely related to this material. It's ultimately going to build up to plotting the capital allocation line, and along the way, we are going to manipulate some financial data and see how R is a super powerful tool for these functions and features. Now, before we get started, the main thing that we need to do is make sure that we have a handful of packages installed. And you can follow along either by typing this code yourself, or you can download this R script and just run it on your own local machine as we work through it in the video. Well, the five packages that we're going to use today are the Tidyverse, Yahoo Financer, Lubridate, SQLDF, and RootXL. So Yahoo Financer is just a package that connects to Yahoo's API, so that way you can download free stock data. It's not the best stock data, but it's good enough for our purposes. And a Tidyverse is a relatively large package that allows us to do a lot of data manipulation. You can manipulate strings, numeric data. It offers a lot of different functionalities to R on top of the base software itself. So for pretty much every project that I ever work on, I will load this. Similarly, Lubridate is another great package that's closely related to the Tidyverse, but as the name implies, it focuses primarily on date data. Now these next two lines are related to the SQLDF function, a SQLDF library, which allows us to incorporate SQL code, which is SQL language or structured query language, into our R programming. For most intents and purposes, you won't need this, but I would like to show you how to use it just in case you're ever in a situation that basic merges in R will not allow you to perform. Now, there is some glitches, or not. It's not really a glitch. It's oh, maybe it is a glitch. It's kind of hard to describe. Well, on a lot of computers that I've used SQL on, for whatever reason, if I don't include the option g sub fn dot engine equals r before calling SQLDF, it will freeze up the computer. Now, I think this had to do with an older version of R, like 4.05 or something like that, which most of us are not going to be on anymore. But just for my sanity, I like to include this option before calling SQLDF. And lastly, we have readXL, which is just a function that allows us to call Excel data and load it into R. Now, with that said, first thing that we need to do is set a working directory that is where we believe most of our data is located around. So I have a little bit of foresight as to what we're going to do, and I have given you access to an Excel file of risk-free rates. And I know that I'm going to have to call that at some point here soon. So what I want to do is make sure I have a working directory that is, or that holds or is close around that particular file. Now let me just load these packages and set the working directory. You can press Control Return or Control Enter or Command Return depending on your OS. The idea is similar across all OSs. And now you'll notice I have my working directory up here on the top of the console. I can change this to whatever I want it to be, but the syntax is going to change a little bit based on your OS and your desired directory. Like if I just wanted this to be in my OneDrive accounts, I would just have this first part. Or if I wanted to be more specific within this course subdirectory, I would add more forward slashes, so on and so forth. Well, let's get our financial data. Just to be consistent with what we've been doing in class, we will call some data for the S&P 500 index. Now, despite the intuitive, or despite being unintuitive, the Yahoo Finance API considers or calls the S&P 500 index the caret symbol GSPC. Well, you may not know that unless you go to Yahoo Finance. And for any of the data that you want to download, you can go to Yahoo Finance and say something like S&P 500 index, or the Nikkei index, or the FTSE 100 index, and it will tell you what its own symbol is. Now, whatever data you want to download, or to get it into R using the Yahoo Financer library, we'll type index $new. And what this does is whenever we assign it an object name, I call it S&P 500 call, and I run that line, notice it now becomes an environmental variable over here on the top right hand side of the screen. Well, I can get the actual data by referencing this object, saying $get history. So you think about it like this. So S&P 500 SP 500 call is kind of like an area code and a phone number. And within that area code, I have a specific function, or a specific number, if you will, that allows me to get to the desired goal, or I can reference, or I can call on the specific data that I care about. Now, within this get history function, there are a lot of different options. You can go over here to the help and say get history, and it should pop up. Okay, ironically it doesn't. However, you can still get to a help function for the Yahoo Financer package by typing in Yahoo to packages, and now you have the whole help file here. And if I imagine, the help would probably be under index, which is what the original function is. Well, within this, there are different options you can call, like the start date for the time series you want, the end date, and the interval. Just to be consistent with what we've done in class, we'll go from 2000 to 2020 with monthly data. However, I'm going to be a little more correct here than what we were in class. So anytime we want to get a full time series of return data, we really want to start our data collection 1 month prior to the time series that we actually care about. So notice whenever I run this line, and I'm going to call this object data so we all know what we're talking about, and if I pull up the data, I have daily price data for the S&P 500 index. Ultimately, I'm going to create returns, and I'll do this in 2 more steps. But what's going to happen is whenever I compute returns for this first observation, because it doesn't have a previous observation, the return associated with observation 1 is going to be an NA, and I'll show you what I mean here in a second. It's always good to get into a habit, though, of looking at how your data is structured, because within R, like also in Excel, there are there are different types of data. You have strings, numeric, dates, and everything in between. And R is going to treat each of these structures differently. Well, you can call the str, or the structure function on a specific object, which data is our data frame, and it will tell you how it treats each of the variables within the data frame. Like date is a POSIX CT structure. Volume is numeric, high is numeric, low is numeric, open numeric, close numeric. And for whatever reason, it considers adjusted close a list comprised of numeric data. Here, we're only going to care about our date and close values. If you're interested in learning more about the list and if that affects anything, always feel free to shoot me an email, and I'm happy to chat and lead you through this some more. But for our sakes here, we're only going to care about a couple things. Looking specifically at the dates column though, POSIX data structures can be kind of wonky to deal with. So I want to convert this to just a normal, standard, everyday date function. And we're going to do a lot of our data manipulation in our next step. Alright, so whenever we manipulate data, we always want to get into a habit of naming our data set. Data is also another object, but it's our raw data. Generally I don't want to manipulate raw data because it's not good practice to do so. So I will take the raw data and manipulate it, but after my manipulation, I'm going to call it something new. So that way I don't rewrite the original data set in my manipulation. So my manipulated data frame is going to be called SP500. So that way we know we're dealing with S&P 500 data. My raw data file, which I don't want to manipulate and rewrite over, but I want to manipulate the data within it, is called data. Right? This is Yahoo Finance's S&P 500 index data. And everything from here on down is the actual manipulation of my data frame. This first symbol, the percent, right arrow, and percent sign, we call this the pipe operator within the tidyverse. If you don't have the tidyverse loaded into a library in your current session, it's not going to work. So always make sure to use the tidyverse library. And what it does is allow us to stitch together multiple commands into one step, which is a massive improvement over base R, where I would have to create multiple different steps and use some rather archaic looking code to accomplish the same goal. Once I know I need to manipulate my data, and I know which data it is I need to be basing my work on, I can actually perform my operations. In tidyverse, we call this a mutate function, and all this does is open up a step where you can list all of the manipulations and the operations that you want to perform. I said a couple minutes ago that I'm not a big fan of the POSIX data structure because it can be a little wonky. So what I'm going to do is a couple things. So I notice first that within the data frame, my dates have timestamps. I don't care about timestamps in this data. I just want the actual day of the observation. So I'm going to strip each of these timestamps away using R's strip time format, or strip time function. And I'm going to feed it a format where my year is first, followed by a hyphen, followed by a month, followed by a hyphen, and then followed by a date, because that's standard R date formatting. And then I'm going to call the asDate function in order for R to convert the POSIX CT data structure without the timestamp into a standard date format. And just like we did in Excel, I want to create a month and a year observation using a month and year function that all it's going to do is look at the dates and then extracts the numeric day and month numbers from the dates. From here, I'm also going to create a month and number observation, so that way each observation within my time series is going to have a unique month node or month number, where January or December 1999 is going to be month 1, then January 2000 is going to be month 2, so on and so forth, to the 3rd, 4th, 5th, so on, all the way until the end, where we should have a total of 253 unique months. This is going to become especially handy if you ever want to do anything in SQL. The last thing I'm going to do is identify a lag value within the price data. A lag is a fancy term that we use to describe just a previous observation within a time series. So if we were to look at January 2000's observation, the contemporaneous close is 1394.46, but the lag close is 1469 and a quarter. In Excel, getting a lag is a situation where you would say equals the previous row, or equals observation in a previous row, and then you would drag it down. Well, R makes it really easy, because all we need to do is say lag of whatever the observation is that we care about, and we'll call it something that helps us remember what the data is. Because it's a previous close value, I'll call it close previous, or close underscore PREV. This is an easy way to get a lag. However, something I need you to remember is this is only beneficial if you have a full time series without missing data within intermediate observations. So not all stock are traded every day. So there's a non-trivial number of assets where we do have missing observations between trade days. And what R would do is say, let's say this observation we're missing. The lag value for the next, or for observation 3, would be missing. But in practice and research, the value that we would actually care about would more than likely be the observation prior that is actually populated. So the lag function is great, but you need the full time series in order for it to be truly useful. Now from here, these are the main data manipulation steps that we care about. And from here, I want to remove everything that I don't care about. Like for our analysis, we don't care about volume, high prices, low prices, open or adjusted close. So what I'm going to do is combine each of these objects that are within the data frame, and using a negative sign or a minus sign before the collection, I'm going to tell it to select everything that is not these column identifiers. I can run this code, and now if we look at the S&P 500 data, this is a much cleaner data set where I have a date of each observation, a close price for the month, a month identifier that ranges from 1 to 12, a year, a unique month identifier that goes from 0 to 253, and I have a lagged observation. But notice my first lag is NA because there is nothing prior to this first observation. Now, another way that you could get a lag observation within R is using SQL. And I'm not going to spend much time talking about SQL syntax. You can just copy and use this as you see fit in your own research or in your own analyses. But the basic structure is this. You could tell R to select something from two different data frames. In this case, the two data frames I'm going to call on is itself, S&P 500. I want everything from one data frame, but only one variable from another. I'm going to rename that variable something different, and I'm going to match on something specific. The matching identifier, or the primary key, you may have heard it called before, is the month number, where I want the month identifier from my left data frame to be equal to the month identifier plus 1 from my right data frame. And all it's going to do is say, hey, for observation 1, or month number 1 in my left data frame, it's going to match to observation 0 in my right data frame. And what this is going to do is give me an alternative method to identify a lag close of month price value. And from there, I can then identify my holding period return, which from class you'll probably remember as being a new value less a previous value divided by the previous value, or new minus old divided by old. Now if I run this, we look at the data, and you'll notice a couple things. First, the close previous column is identical to the lag close column. That's exactly what we would expect. Close previous was created based off of the lag function used on a full time series with no missing observations. Lag close is a way to make sure, or is based off of SQL DF, which is a way to make sure you're getting your actual, or getting the proper lag values. And actually, let me correct something real quick about the lag function that I said previously. Lag, what it's going to do is take the previous non-missing observation. I believe I said it would take the previous value, even if it is missing. That is incorrect. I do want to correct that mistake. Whereas in practice, a lot of times in our trading data, when things are traded infrequently, we do care about a missing observation, which is why we would want to use SQL there instead of just the normal lag function. But either way you choose is okay. You just need to be able to justify your reasoning. Your holding period return afterwards, though, is nothing mysterious. It's just the formula that we've used in class so far. And we'll get the same value for our return no matter which data we choose. Now, one last thing for me to mention about SQL is I use what's called an inner join, because it's going to remove observations that have no match. For example, that's the reason why I no longer have an observation from 1999, because as you recall from a few minutes ago, it had no lagged close variable from, or there would be, there is no lagged observation pre-1999. So it gets dropped from our sample. Now from here, you can now use R in all of its glory to identify means, standard deviations, distributions. You can aggregate your data and do everything that Excel could do, but in my opinion, it's quicker and it's cleaner. If you want to take the average of something, or the arithmetic average, let's say I want to know what the average monthly S&P 500 return is, I can use the mean function. It's also a good habit to get into to using the na.rm function and setting it equal to true, or option within this function, because if there's a chance that data is missing, R will return a missing mean. However, for our data series, there's nothing missing. We don't need to worry about that, but I just want to show you so you can get into the habit. Now, if we use the mean function, we can see the average monthly return for the S&P 500 over our time series is about, 50 basis points or so. The standard deviation, called by the SD function, is about 4.4%. Now, if we want to plot the distribution of returns, I'll fix this little misspelling here. We can use the ggplot function. And the syntax is meant to be clean. Anytime you want to plot something using ggplot, you first call ggplot. And you tell it the data frame where all of your data is housed within. In this case, it's the S&P 500. I care about a histogram because I want to see the distribution of returns. So we'll call geom histogram and then say AES something. AES is short form for aesthetic, and your inputs are going to change based on the type of plot that you want to present. Histograms only have one input variable. It's going to be the X variable, which in our case is going to be the holding period return, or HPR. And we can feed a lot of different options into geom histogram. Just to make things pretty for our picture in the video, we're going to say bins equal 40, which is going to present 40 different bins within our histogram figure. You can change the bin width to say, like, hey, I want each bin to contain only 50 basis points of a range, or 1% range, so on and so forth, but I'll leave that to you for your own time. ScaleX continuous is an option that we can call, and it really is an additional function that we can call, that trims our plot to be within certain limits. And our limits here are going to be between -10 and 10%, just so we don't have super long tails in our figure. Now everything underneath this is purely idiosyncratic. So theme BW makes my figure follow a black and white theme. I like it because it's pretty. The theme function allows me to adjust the position of the title. HJust here, or element text with the HJust function option, setting it equal to 0.5 centers my title. Axis.text.x will angle, or allows me to adjust my x-axis. Here I put my ticks at a 45-degree angle, and then I remove the title. Labs is similar to the theme function, but Here I'm using it to just identify the title and to name the title of my plots. One thing to keep in mind when using ggplot though is you stitch together each additional option or function within your ggplot with a plus sign, which is different from a mutate step or whenever you're dealing with the actual data structure itself or the data frame itself, which is using the pipe operator. Now if I plot this, control return or control enter, command return, you can pull this up and now we have a pretty distribution of S&P 500 monthly returns. It has an approximate bell-shaped curve, right? And if we were to extend these tails past -10 and past 10%, we would have thinner tails as we go to the left and thinner tails as we go to the right. It's not perfect normality. Actual data never is, but it looks like it's good enough. Now let's aggregate our data from our monthly frequency up to a yearly frequency. I'm going to call my new object S&P 500 yearly, base all of my manipulations on the S&P 500 data frame, and because I want yearly data, I'm going to group by year. And what it's going to do is tell R to pull data together from the year 2000 and then pull together data from the year 2001 and then 2002, and it's going to treat each of these as its own tiny little data frames. I care about the geometric mean or the geometric average of my monthly returns because I want to aggregate it up to a yearly observation. I do this by calling the exponential of the sum of the log of 1 plus my monthly holding period returns and subtract 1 from that calculation so that way I can get it into a percentage return. One thing to notice here is it's super important to include the na.rm equals true option because sum is a lot like the average, the mean and the SD functions, where if there is missing data, it will return missing for the whole observation, even if it's just for one missing NA value. So it's good practice to include this here. Next thing I want to do is count my number of observations within each year grouping, because whenever we aggregate volatility from monthly to yearly data, we need to take the square root of the number of observations and multiply it by the standard deviation of monthly returns. Because remember, risk has a time component to it, and we need to account for changes in granularity. Now if I run this, you'll notice over here on the top right hand corner of our screen, our S&P 500 data, which had 252 observations, now only has 21, which makes sense, right? Because we have now one row for each year. Now I don't know about you, but personally I find this to be significantly easier than aggregating data in Excel. Whereas Excel, you have to put in a lot of if statements and drag and drop and a bunch of other things. Here in R, I just tell it to just group by whatever characteristic I care about and perform the same data manipulations that we use on a day-to-day basis in finance. Now, my yearly data frame is not complete because I do care about the risk-free rate, because ultimately we're going to compute excess returns. So I'm going to call my risk-free rate data set, which is an XLSX format. This can be anything. It could be a CSV, text. R has a function to help read in every single, or pretty much every single type of data structure. But from here, once you know the data structure, you know where you know the data formats, XLS, XLSX, or CSV, or whatever. You know the title of your data set. You can tell R to read Excel or read CSV, read data, etc. And it'll read it in for you. One of the cool things about R that's really easy to do in comparison to a lot of other statistical programming languages is the ability to quickly rename observations. So if I pull in this data set, if I pull in this file, you'll notice RF underscore rates is in the top right hand side of my data set. And I have two columns, year and risk-free rates. But notice risk-free rates is not a very pretty name. It has a hyphen in it, which R is not a big fan of. And both of these are in capital letters, which is no big deal. However, sometimes people like their column or their variable titles to be in lower cases. But one thing we especially don't like is having hyphens in variable names. So I can tell R immediately after reading in the data that I want to rename my columns. Renaming columns is really easy. All I need to do is say rename, feed it my new name that I want the data to be, set it equal to the old name, or I can set it equal to the column position, which is really unique and very handy, especially if you're dealing with government data, which a lot of times has super long names or a bunch of just like string identifiers for variable names. And if you don't want to tell R, hey, rename this column XYZ 1, 2, 3, 5, 6, 7, 8, 9, 1005, so on and so forth. If you know the column position, you can say, hey, rename my second column to be RF rate. So now notice, these are our old column names. I'm going to rerun it. And now it's pretty again. I have one observation for each year. And now what I'm going to do is combine my market data to my risk-free data. Now, instead of using SQL to do a join, I'm going to use the tidyverses version of a join, which here we're going to use a left join, but you can use an inner join, etc. Inner join is going to give you the same result because there's a match for every observation. And what I mean by that is if my left data frame is my market data, I'll move this over, and my right data frame is the risk-free data, excuse me, you'll notice if we were to join together the data on year, I'll have a unique match across both data sets. Here we'll tell R to match on just the year observation. And excuse me, I feel like I got something in my throat here. We will ultimately get each risk-free rates associated with each year over into this data set. You have different ways of naming a new data set. You can, if you wanted to, you could call this S&P 500 Yearly 2 or new or something like that. But I'm just going to rewrite the old data sets, which some people may say is not great practice. For me and for you in our practice here, it's not going to make a major difference. And from here, after we join, we're going to make a quick manipulation by mutating we're going to difference our yearly return and the risk-free rate to get our yearly excess returns for the S&P 500. Now notice we now have the risk-free rate column and an excess return column, which just tells us how much greater or less the S&P 500 return is over the risk-free rate for any given year. Now we're on the home stretch. Let's create a portfolio. You can choose any year for your own analysis, but let's just choose our expected portfolio performance off of the year 2019. What I'm going to do is combine a couple steps that we've talked about already. What I'm trying to do is identify just my assumptions of portfolio performance based off of 2019 data. Let's say you have a client or a family member, or just for your own curiosity, you want to create your own portfolio, and you want to know expected performance, or you want to project your expected performance based off of a given cross-section of data. Cross-section meaning within a year. Well, we choose 2019 because it's fairly recent, but at this point it's also about half a decade away. Or, yeah, it's about half a decade away. So what I'm going to tell XR to do is look within my S&P 500 yearly objects and filter my row that is just on 2019. But for the sake of assumptions in portfolio creation, I just care about a handful of things. My market return for that year, the market volatility, and the risk-free rates. So I'm going to select just these three columns. And now what we have is our expected performance on the market and the risk-free rates for this year, for 2019. It's a one-row data frame with three columns. Now what I can do is create a data frame for my expected portfolio performance. Now, I'm going to build this from the ground up. This may seem a little advanced, but I promise you can get it. R is meant to be read without really much thought behind the functions, but I want you to notice everything that we've done, or everything is written here. After this first step, from here below, the general structure is something that we've already discussed. This first step, though, is the object that I'm basing all of my following steps upon. And what I'm telling R in this first step is to create a data frame that's based off of a sequence of numbers from 0 to 1, going in 1% increments. If you want to see how this looks, notice I'm given a column title, a variable name that is not very pretty, but I have a sequence of numbers that go from 0 to 100%. This is a parallel to Excel's sequence function. And what this has done is initialize a new data frame with allocations for just one asset. Let's say we're going to call this the allocations for our first asset being the risk-free assets. If I look at this data frame again, let me exit out of this, rerun it. Let's see. I was including the pipe operator by accident. Now notice my new column is called RF for the risk-free rate, but that's not the portfolio, right? We still need the market asset, we need expected returns, we need volatility, etc. Well, because we're dealing with just a 2-asset portfolio, my equity weights is just going to be the complement of my risk-free weights. So I can generate a column called equity and say 1 minus the RF weights will be my equity weights. From here, we would then have weights or supposed weights for both the risk-free asset and the equity asset, which means we can now compute expected portfolio returns. Portfolio returns, though, are going to be the weighted average of the constituent returns of each asset within my portfolio. Or it's going to be a weight times an expected return plus a weight times an expected return. So notice RF here is the variable within my port returns objects. Equity is the weight for the market asset within my port returns objects. But notice I'm multiplying each of these weights by an object that's outside of this data frame that I'm calling. That's something really powerful about R, because what I'm telling it to do is multiply each weight within this data frame by the expected returns on each of these assets that are found in another data frame. Notice exp underscore rets is the data frame of assumptions, and then $sign calls a specific variable within that object, and those two specific objects are the risk-free rates and return year. If you didn't want to do that, that's perfectly okay. You could rename this to say something like the risk-free rate times the 0.0206 plus equity times the expected return on the market. You could do that too. Both ways are equivalent. However, this way is much more dynamic and allows for more flexibility. It's not quite as readable, but it's a little more powerful. And your own programming style is going to differ as you develop your skills over time. And it will also differ for whatever your project is. Next, we can compute the portfolio volatility, which, because we're dealing with a two-asset portfolio that's comprised of the risky and the risk-free asset, the only volatility we care about is that of the market assets. Remember from class, the portfolio volatility for a complete portfolio is going to be the weight of your market asset multiplied by the volatility of the market asset. And once again, if you don't like this notation of calling another object or calling another variable within a different object, you could just say equity times whatever the volatility is. These last two rows are just formula. So the excess return is going to be your portfolio return minus the risk-free rates. I call the risk-free rate from the expected returns object, but once again, you could just say portfolio return minus 0.0206. And then the Sharpe ratio is going to be the ratio of excess returns divided by your portfolio volatility. Now, if we look at this data frame, it is now complete. We have different weight combinations, different expected returns, and different linear combinations of expected returns based off of different weight pairings. Notice the Sharpe ratio is the same for each of these observations except for the very last one, which has no volatility because it's purely concentrated in the risk-free asset, which is exactly what we would expect, which implies that what we're dealing with is a capital allocation line. And all it does, remember, capital allocation line does not have anything to do with diversification, but everything to do with relating a given level of risk with an expected return. And you can see this relationship by plotting each of the expected returns with the volatility of each weight pair. We can plot this using a scatter plot called ggplot, the object that houses the data we care about. GM points is for scatter plots. AES, our X variable, is portfolio volatility. If you want to, you could say X equals. Our Y variable is port RETs. But you don't necessarily need the X and the Y, because R is going to assume what comes first is X and what comes second is Y. And everything that follows is purely idiosyncratic. I like the theme black and white. I like a center title. I don't necessarily like X-axis titles for a lot of things. And my title of the overall plot is a capital allocation line for complete portfolio, aka the capital market line, because one asset is the market assets. This little text here is what we call regex, and it tells R to split our title into two different lines. You can plot this, and wouldn't you know it, we have a straight line. The slope is going to be the Sharpe ratio, and it tells you that for each and every single possibility, each and every combination of the risky and the risk-free asset here provides you the same level of reward for a given level of risk. So intuitively, it's totally up to you to choose where you fall on this line. Sure, you can reach for higher returns, but you're going to be accepting a higher level of risk. Or you could have less volatility, but get less return. And that's what we talk about, or that's what we mean when we talk about a risk-return trade-off. Now, if you want to make this plot a little bit cleaner, you could change our axis title on the X to, you could say something like SD port returns. Oh, whoops, messed that up. Did I mess it up again? Yes, it looks like I did. Let me Control Z this. Oh no. Actually, if you want to make it a little bit cleaner, just remove that, and your X-axis title is going to be port volatility, which shows you that risk-return trade-off just a little more clearly. Now, with that said, this is a pretty much one-to-one comparison of everything that we did in Excel for Class 6, and it also presents how to identify the capital allocation line based off of assumptions in R, and it also shows you how to manipulate financial data using what I consider to be the most powerful statistical programming language currently at our disposal. As always, if you have any questions, shoot me an email, reach out, and I'm always happy to give you more info and walk you through these ideas one-on-one. Thanks, y'all.